So, welcome everybody. It's a big pleasure to have José Alberto giving us a review of the present situation of the CMB. So, as most of you know, in this field, the situation has changed dramatically in the last 10 years. I think it's basically just knowing that there was anisotropies to have now something like it's called the cosmology of precision, so where you can extract the parameters with high accuracy. No? So I have to acknowledge, or the Commission de Seminario have to acknowledge José Alberto for a brief note and giving us a talk so quickly, and I think you can all enjoy, because José Alberto is a good speaker. So.
Thank you very much for the presentation. So the first thing is that this talk that I'm going to present you here is a talk that I delivered a couple of weeks ago in Granada in a meeting, Cosmology Across Cultures. So all the transparencies that you will see here are basically transparency from that talk, but complemented slightly with some another slides that I added. So the outline of the talk is the following. The idea is that I'm trying to review the past and present and future situation of the field. But before that, I will make a quick introduction to the cosmic microwave background. Probably all of you know most of the things that I'm going to review here, but I think it's important to, not everybody is expert in this field, so it's good to go through the basics of this field. So I will quickly review what is the CMB, and in particular the anisotropies, which are going to be the central part of my talk, and what are the relevance of these anisotropies for cosmology. And then we will go through the three stages of the talk: past, present, and future of this field. So as an introduction, you remember that the cosmic microwave background was predicted by Gamow back in the 46. He was studying a completely different problem he was studying the origin of light elements in the universe, and he needed to introduce a model with an early stage in which the universe was very hot, in order to explain why we can see light elements in the universe. This prediction was also done later by Doroshkevich and Novikov. In 48, Alphen and Hermann were able to predict numerically what should be the temperature of this cosmic microwave background radiation, following the basics of the model that was proposed by Gamow. As you know, the CMB was discovered in 64, but the paper was published in 65 by Penzias and Wilson. You can see here the picture in the back is the antenna in Bell Laboratories that they used to measure this radiation. And because of this discovery, they got the Nobel Prize in 78. Quoting the original paper of Penzias and Wilson, what they found is a radiation which is isotropic, unpolarized, and free from seasonal variations. These properties are essential in order to ascribe this radiation to the cosmic microwave background, to the prediction of the model of Gamow. As you know, there was a paper following immediately the paper of Penzias and Wilson by Dicke, Peebles, Ross, and Wilson, where they interpreted this radiation as the cosmic microwave background. So the basic properties of this radiation are summarized here. It has to be a black body. It should respond to a black body spectrum, and should be highly isotropic in order to be the remnant of the hot Big Bang. So these 2 points were in fact very soon established. The fact that the CMB is a black body spectrum, there were several measurements in the following years after the measurements of Penzias and Wilson, and already in 67 we had measurements of the spectrum, all of them showing consistency with a black body of 2.7 Kelvin. A few years later, you may remember in 72, there were some papers about the measurements of the CMB temperature using one particular line of the CM molecule. So all these measurements already by the end of the 60s, beginning of the 70s, were showing that the radiation was having a black body spectrum. The fact that this isotropic was also soon established, I show here some measurements of Partridge and Wilkinson in 67. 2 years after the discovery, where they were showing that the variations that you can see here are basically due to the atmosphere. But if you take into account the error bars, they were able to show that there were no evidence of anisotropies at the level of 1% already 2 years after the discovery. So by 68, we already had this picture that the CMB was isotropic, highly isotropic, and responding to a black body spectrum. So this was the situation in 72. This is a picture from a paper of Longuer and Sunyaev, where you can have, when you have what is the spectrum of the background radiation, the whole spectrum. I mean, if you look to a region of the sky where there is no sources, you can see here the black body radiation, and the rest, well, for example, this is what we call today the cosmic infrared background, that we know that nowadays can be practically resolved in terms of galaxies at high redshift and so on. But we already had this picture in 72. So, as you know, the CMB is one of the basic pillars of our model of the whole Big Bang model of our understanding of cosmology, together with two other key observational issues, which are the expansion of the universe, which is observed as the Hubble law, and the measurements of primordial nucleosynthesis. Within this model, we understand the CMB as the remnant. The radiation was left once the universe was sufficiently cold. This was happening what we call the recombination area. When the universe was having a temperature of around 3000 Kelvin, this temperature was low enough to permit atoms to recombine, to form in neutral atoms. And in that moment, photons, we were interacting with electrons through Thomson scattering, are free and can travel freely to us. So, using this number, 3000 Kelvin, using that today we observe the temperature at around 3 Kelvin, and given that in a hot Big Bang cosmology, a black body radiation, the temperature is diluting with expansion as 1 plus C, we can say that the CMB is a picture of the universe at redshift 1000. So it's the let's say the picture of the most distant picture of the universe that we can have in some sense. Okay, all this situation was much more firmly established once we had the results of the COBE satellite. COBE was having 3 experiments on board. You know, well, we probably know COBE, the satellite of NASA that was launched at the end of the 80s. And the 3 instruments were the differential microwave radiometer, the diffuse infrared background experiment. This was dedicated to far infrared, and FIRAS, which was dedicated to measure the spectrum. And basically the results of these 2 instruments were essential for our understanding of cosmology. The first one, FIRAS, was able to determine with extremely high accuracy the spectrum of the cosmic microwave background. You can see here, these are error bars. I mean, these are measurements, and direct measurements of FIRAS. You see here that the deviations with respect to a black body are extremely small. I mean, FIRAS was able to set deviation of the order of 10 to the minus 5. This is the best, let's say, most accurate black body spectrum that we know in nature. Even in laboratory, we are not able to reproduce a black body spectrum with such a high accuracy. So this was a key result of COBE, and the second one is the fact that they were able to set the limit, to set the level of anisotropies. I will spend a couple of minutes with this slide because of the importance of anisotropies and because it's going to give you an historical perspective. Imagine that you take an experiment like COBE, DMR, which is measuring the sky in the microwave, let's say 53 gigahertz. You take a map of the whole sky, and what you see is this. This is isotropy. This is evidence that the universe in the past was extremely homogeneous and isotropic. This is what Arnold Penzias and Robert Wilson were discovering. If you subtract the constant value of 2.728 to this image, you will see this. You start to see deviations with respect to the isotropy, and you see that the level now is of the order of millikelvin. So So you have to go 3 orders of magnitude below in sensitivity in order to see these differences. This was measured by the first time at the end of the 70s, beginning of the 80s. We now understand this structure as, you see that it has a dipole shape. We understand this structure as produced by the relative movement of the Earth with respect to the cosmic microwave background. Okay? If we subtract this dipole component, we again have to go 3 orders of magnitude below to start to see anisotropies. So, you see, now the level is of the order of 20 microkelvin, so deviation in one part in 10,000. And this is what the COBE measured. What you see here is the map in galactic coordinates. So this red blob is the galaxy, the emission of the galaxy in microwaves. But all the spots which are seen outside the galactic plane are primordial in origin. So why it is important? Well, because of these 2 discoveries, you know that in 2006 the 2 PIs of these 2 instruments got the Nobel Prize. So why do we expect to see anisotropies in the CMB? Well, as I said before, if the CMB is a picture of the universe when it was at a redshift 1000, this means that we should see there the seeds of the structures that are going to evolve and form the galaxy, supercluster of galaxy, and so on that we see in our present universe. So it's important to remember that our model of structure formation is statistical in a sense. This means that the model is not predicting where we are going to have a galaxy, for example, but it's going to predict the statistical properties of the distribution. In terms of the CMB, it is not going to predict where we have a positive spot or a negative spot, but it's going to predict the statistical properties of the distribution of the spots. So, having this in mind, we only need 2 basic ingredients in order to fully describe the cosmic microwave background. The first ingredient is the initial conditions, which are normally provided by inflation. And the second ingredient is a description of the background. In this background, the fluctuations are going to evolve and are going to form the structure. Okay? So once we have these 2 ingredients, it's relatively simple to compute what are the anisotropies that we expect for a particular cosmological model. I'm not going to enter into the detail here. You have a summary. Normally, as anisotropies are classified in terms of anisotropies which are produced at redshift 1000, or anisotropies which are imprinted in the photons once they are traveling toward us. So this classifies anisotropies into primary and secondary. I will not enter into the details. You can ask me about this if you want, but I will concentrate in the observational part of this. The key idea is that once you compute all these statistical, what is the prediction for a particular model, all the information can be encoded into a single statistical quantity, which is called the power spectrum. What is the power spectrum? So basically, you have a given map. You can decompose this map in spherical harmonics, which is equivalent to make a Fourier transform of the map if we were in a plane, in a flat space. But I mean, given that you see the map in the sphere, the natural symmetry is to do the composition in spherical harmonics. So if you take the coefficients of the spherical harmonics and you compute the square modulus of that is what we call the power spectrum. And why is it so important, the power spectrum? Because it is going to encode all the cosmological information, all the important information about the cosmology. Okay? So you can see here in this picture what are the predictions for different models, for completely different cosmologies, what are the predictions for the power spectrum. As you see, I mean, it is not obvious that we should expect, it was not obvious in the 80s, that we should expect, I mean, peaks. Not working. Okay, it was not obvious that we should expect peaks in the distribution, in the angular power spectrum. We will see that this is what we observe today, but in principle you see that there were models that, for example, cosmic textures which were not producing peaks. And even the number of peaks, it is something which is not fixed. I mean, if you change, for example, the amount of variance, you can decrease and practically make disappear the even peaks. So the basic idea is that if we are able to measure this, we can extract the extremely important information about what are the values of the parameters, what are the models that we are understanding. You know that the standard model is the lambda CDM model, and the basic parameters which are describing this model are summarized here. Just as a reminder, you have here these parameters. So before ending this small introduction, I would like to comment one additional thing that probably you have not heard too much about that before, and it's the fact that CMB anisotropies are expected to be polarized, and in fact they have been measured to be polarized. The mechanism to produce polarization is relatively simple. If you have an intensity distribution which is anisotropic, and in particular, if this distribution have a quadruple anisotropy, you expect to have anisotropies just because, I mean, imagine, if you are looking at a particular direction and if you are having an excess of photons in this direction than in this direction, given that the Thomson scattering is producing polarization, you will have an excess of photons with this direction of polarization with respect to the orthogonal. So if the radiation field is anisotropic, you expect to see polarization. The important thing is that this polarization is generated through a scattering process. So this means that we are going to see linear polarization. So in terms of the Stokes parameters, this means that we will have Q and U, but we will not have B parameter. We will not have circular polarization. In the CMB, we are not used to work in terms of Q and U because we want to produce maps of the full sky. And as you know, Q and U depend on the reference system. I mean, you need to specify a particular reference system in order to define Q and U. So what we do is we make a coordinate transformation of this Q and U into two quantities which are scalar and which are called E and B. The reason that, I mean, you have to think in that as a coordinate transformation. It's non-linear coordinate transformation, but it's just a coordinate transformation. So having E and B, we can predict what is Q and U. But the important point from the physical point of view of this decomposition into E and B modes is that these modes are connected with the physical processes that are producing the polarization. So E modes, we call that E modes because are analogous to the gradient component of an electric field. So this means that we don't have, an E mode has no rotational, so an E mode is this thing on the left, and B modes, they have no divergence, okay? So, having introduced these two new fields, we have now, instead of one, we have 4 power spectra. We have the temperature power spectra that I was showing before, we have the E power spectra, the B power spectrum, and the combination TE. All the other combinations are 0 because of parity. So, as I was saying, the important point from the point of view of physics is that scalar perturbations, I mean normal fluctuations, cannot produce B mode at large scale. So, in order to have a B mode at large angular scales, we need tensor perturbations, and tensor perturbations means gravitational waves. I will come to this point in the last part of the talk. Okay? So, this was more or less this introduction. So I'm going to the main part of the talk. First part, establishing the standard model. The past of the field. I like to put this title because I consider this epoch, I mean, at the end of what we call now the past of this research, we established already what is the picture that we today are confirming. We could start, I mean, with all the slices that I was showing with the discovery of Penzias and Wilson and so on, but maybe the most important milestone in this study was the detection of anisotropies by COBE. But COBE was not the only one experiment. There was an enormous observational effort, from the discovery of the anisotropies until COBE and beyond COBE and even nowadays. And here you have a summary of some of the experiments which are classified in terms of the technique that these experiments are using to detect the anisotropies. So basically I'm classifying in terms of radiometers. For example, the Tenerife experiment was one radiometer. Bolometers, basically these are the balloons experiments. You will remember probably boomerang. And interferometers. One example is the BSA, which is the one on the right. I'm going to speak about that a little bit. So maybe because of we are at the IC, the most important instrument after COBE was the Tenerife experiment. You know that this experiment started in '84. It consisted in 3 radiometers measuring at 5 degrees angular scale. This experiment was a collaboration between Manchester, Cambridge, and the IC. And before COBE, the Tenerife experiment was giving the best upper limits on the level of anisotropies. And immediately after the COBE results, the Tenerife experiment confirmed the level of anisotropies in this paper in '94. And this red blob, which is marked there in all the 3 frequencies of the Tenerife experiment, was also detected in COBE. Okay, so this was an independent confirmation of the level of anisotropies, and an independent confirmation that the features in the sky that they were observing were the same, using different observational techniques and so on. Okay, so this slide is trying to summarize what was the observational status in 2000. It looks a bit like a mess, no? There are a lot of points, many experiments. You see at the beginning the points of COBE in black. You see in green the one of the Tenerife experiment. And there were several experiments which were producing a few of points. If you take all of them in total, you have evidence for the presence of a peak. But it was difficult to do this combined study because of a problem of cross-calibration. You have to think that we are speaking about 20, 40 microkelvin. So this is so small temperature level that you need extremely good cross-calibration between experiments. So, it is not easy if you are comparing 2 experiments which are calibrated in a completely different way to put them in the same vertical scale. This problem was solved because after 2000, a number of experiments were producing. A single experiment was producing the whole measurement of the first peak, second peak, and so on. Starting, for example, with balloon-borne experiments, you will probably remember the results of Boomerang in 2001. This is the spectrum of the second analysis that they do, where a single experiment is tracing the first peak, evidence for the second peak, and third peak. If you make an analysis of this map, you can infer properties of the universe, of cosmological parameters. Maybe the most important is the fact that the CMB already in 2001 was showing that the universe is flat, omega total equal 1. This is something which is very clearly established by the cosmic microwave background, and is connected with the fact that if you remember in the plot of angular peaks, the first peak is the more dominant, okay? So that means that if you look at a map, the most frequent spot that you are going to see is the spot which is connected with the first peak. So if you are able to measure what is the characteristic size of this spot, you immediately will have a measurement of the total geometry of the universe. Above you have the Boomerang map, and below you have the typical size of a spot that you expect for a flat universe, for a closed universe, or for an open universe. So the typical size of the spots was clearly pointing to a flat universe, omega total equal 1. And this has been established by many other experiments. Immediately after Boomerang, Maxima, another balloon-borne experiment, was determining this omega total equal 1. And apart from balloon bonds, we also have a large number of interferometers measuring the power spectrum. DAISY, for example, which was an experiment run in the South Pole by University of Chicago, also a compatible result with the total geometry of the universe. CBI, this was placed in Chile, and the BSA that you will remember probably from several talks here at the Institute. Just to remind you, the typical maps that we are obtaining with the BSA, these are the results in 2004 for the anisotropies, and it was the power spectrum, for example, that we had in 2004. The important point is that if you make a comparative study of all the cosmological constraints from all these experiments, you see here, this was in the first release of the BSA data in 2002, but the paper appeared in 2003. You have here the BSA, the boomerang, maxima, DAISY, and the combination of all the experiments. You see here that a number of experiments which are using completely different observational technique, which are observing different regions of the sky. You have DAISY, which is looking in the South Pole, BSA, which is here, looking in the North Hemisphere. Different experiments, different techniques are giving a consistent picture. So you see a baryon content which is compatible with nucleosynthesis abundance, and a universe which is flat. So this is why I was calling this first section establishing the standard model. So the basic picture was already in 2003 was already very clear. You have also a picture, again, BSA, boomerang, maxima, DAISY, and the combination of omega mater and omega lambda. In this case, you need to introduce some additional information. For this analysis, I was incorporating a supernovae, but you can do that using, for example, the constraints of the Hubble Space Telescope. Using this combination, you already had this evidence of 30% matter, 70% cosmological constant. So, present, as Nacho was saying in the presentation, we are in the many people are calling now that we are in the area of precision cosmology. So what does it mean, precision cosmology, from the point of view of the CMB? The picture is clearly dominated by the results of WMAP. The first result came in 2003, but the experiment is still running and producing every 2 years, is producing a new release. I'm going to show you here the results of the release of this year, March 2008. So basically, to remind you, WMAP is an experiment which is mapping the sky at 5 frequencies, starting 22, 33, 41, 60, 90 gigahertz. You see, it's a pity that this is not working. But you see here, for example, the galactic plane, how the galactic plane is decreasing with, is shrinking when you go up in frequency. This is because at low frequencies, the emission is dominated by synchrotron. If you go to high frequencies, this synchrotron emission is disappearing. I think I can... Yes. But, for example, you can look at particular features which are far from the galactic plane. You can see particular feature. For example, look at this negative spot, which is identical in intensity in all frequencies. These are the primordial anisotropy, something which is independent of frequency. Any other thing which is dependent of frequency has to be galactic. These are the maps in intensity. WMAP was also producing polarization maps. You have the equivalent here in polarization, but keep in mind that at these angular scales, basically all the polarization that you see here is dominated by the galaxy. Okay, so this is basically mainly due to what we call foregrounds. Okay, so what is the current situation of the power spectrum? Considering large angular scales, this is summarizing this result of WMAP from this year. So I would say that maybe the most important point is that the most important result of WMAP is that it is confirming with very high precision the standard picture that was determined by some experiments a few years ago. You have in this picture something like 300 statistically independent points, only from WMAP in temperature. The red line is a model, is the lambda CDM model, which has only 6 free parameters. Okay, so you are only the temperature data, 300 independent data points, can be fitted with 6 parameters. But not only that, using the polarization of WMAP, you can determine with relatively good accuracy one of the 3 other remaining power spectrum of polarization, which is the cross correlation between temperature and the E mode. The green line that you see here is not a fit. If you take the lambda CDM model, which you fit in temperature, and you make the prediction of what should be the polarization, you have the green line. So the green line is not a fit to the data. It's what you will expect to measure, and it's in fact what you are measuring. So this is showing that, I mean, we are understanding in detail what is the physics of the anisotropies. Okay. Yes. Mm-hmm. The small angular scale, all this part is produced in recombination. But this bump that you see here, this is local. This is produced at low redshift, and this is connected with the reionization of the universe. I was not mentioning this in detail, but measuring how this bump is going up, you can infer a measurement of the epoch of reionization. From the recombination. I mean, in the model you can compute simultaneously. I say that this comes from recombination, Resi 1000, this part. Okay, so I mean, it's something relatively, I mean, easy to explain. I mean, all these peaks comes from acoustic oscillation I mean, the photons are oscillating in the potential wells of dark matter. Due to gravity, they try to compress. Due to radiation pressure, photons try to escape. They expand. So these oscillations that you see here is just a question of acoustic oscillations. The polarization, in some sense, is connected with the velocity of the particle. So you will expect that to have more polarization in those places where you have a larger velocity. So in the maxima and in the minima, you have a minimum in the velocity. In the intermediate stage, you should have a maximum in the velocity. I mean, just if you think in the oscillation. So the prediction of the model is that the peaks of the polarization should be shifted by half the phase with respect to the peaks in intensity. And this is what you see. The peak in polarization is exactly coinciding with the half of the position where you have the peak in temperature. So this is a prediction that you can do from the epoch of recombination, from Resi 1000. If you want, we can discuss a bit more about that. Okay, so this was concerning large scale. At the small angular scales, there are a number of experiments which are measuring the angular power spectrum. Of course, we have the results of 2004 of VSA and the ACBAR 2008 results from this year, which are already tracing a number of peaks, third, fourth, fifth, and so on, and the decay that we expect, the damping that we expect of the anisotropies. So this is concerning temperature. What about polarization? We already saw that WMAP is starting to measure TE. There are two more power spectrum. One is EE. These are the experiments which up to now have measured the E mode. As you see, the situation is not clear. Again, this line is what you expect from the lambda CDM model. But I mean, the error bars are still not sufficient. I mean, we are basically in the same situation we were 8 years ago, but with the temperature. But I mean, you will that it should improve soon in the coming years. And concerning the B mode, polarization, I will speak about that a bit later, we don't have detection yet. Okay? So we have an upper limit, the best upper limit, which is coming from the WMAP results of R.4. That means that at the most we expect 40% of contribution of gravitational waves to the total anisotropy. Okay? So R is the fraction, the relative fraction of tensions with respect to scalars. So summarizing, this is the table which is describing the basic parameters which are obtained nowadays with the analysis of WMAP data. The first 6 are independent, are the 6 parameters of the model. All the parameters which are below, sigma 8, omega matter, Hubble constant, and so on, are derived parameters. Okay, so we only need 6 parameters that we fit. All the rest are derived parameters. So all these parameters are basically confirming the standard picture, what we call the concordance model that we have already for several years. So this picture of 70% dark energy, whatever it is, 30% dark matter, whatever it is. Okay, and this 5% of baryonic normal matter. So, okay, we don't understand what is this dark energy. We don't understand what is dark matter. But we know that with this six parameter model, we are able to fit the CMB, but we are able to fit the data from large-scale structure, the data from supernovae. We are consistent with primordial nucleosynthesis. We are consistent with the measurements of the Hubble constant. You probably remind a lot of measurements of omega matter or other parameters coming from large-scale structure. I will go quickly through 3 results, just which are one of the newest. One is baryonic acoustic oscillation. In the same way that we have acoustic oscillations in the power spectrum of the CMB, we expect the same in the distribution of matter. Okay? Again, this red line is not a fit to the data. It's the prediction of the lambda CDM model that you fit in WMAP, what you will expect to see in the distribution of matter. And you see that both the results of the 2DF survey and the Sloan survey are consistent with the prediction of the lambda CDM model inferred from the CMB. Second one is lambda, the cosmological constant and the total curvature. You see here that the CMB alone is not able to determine simultaneously both parameters. But if you include any of the other data sets, HST means the Hubble Space Telescope measurement of 72 plus minus 8, supernovae result, baryonic acoustic oscillation. If you include any one of these, you already have, with very high significance, that you need a cosmological constant different from 0. And you have this with many independent. You have this with WMAP, with the Hubble, or using supernovae, or using baryonic acoustic oscillation. So different experiments are coming to a common picture. You can do the same if you want to study what is the nature of the dark energy. And for example, in this plot, this is represented the cosmological constant, and in the vertical axis is the equation of the state, which is describing the cosmological constant. The bottom line of this slide is that up to now, the only evidence that we have for a cosmological, for this dark energy is a cosmological constant. We don't have evidence that the equation of state is different from a lambda term that was originally introduced by Einstein. Okay, so it seems that all these experiments are having a concordance picture, but it's not everything so clear in the CMB data. You will probably remember one seminar 1 year ago by Enrique Martinez Gonzalez, where he was presenting some results about anomalies in the WMAP data. There are some features in the WMAP data which cannot be easily interpreted in terms of the standard lambda CDM model. The first one that Enrique was presenting here was a negative spot in the south hemisphere, which is not easily associated, cannot be associated to a standard lambda CDM model. There are also, if you make a detailed study, an asymmetry in the distribution of a slight asymmetry in the distribution of power between the north and south polar hemispheres, and some other results. For example, if you study the low multiples of the observed map, I mean L equal 2, L equal 3, the quadrupole and the octupole, you obtain that they seem to be aligned. And this is not easy to explain. This is not relatively easy to explain in terms of standard analysis. Okay, this is just to transmit the idea that there are still some open issues. So let's go quickly to the last part of the talk. Future, challenging the standard model. So we already have something which is well established by the WMAP data. What is next? So in this transparency, I'm trying to summarize basically all the results that I was presenting you from the discovery, the measurement of the dipole, large-scale anisotropy level, and so all the subsequent discoveries on this field. What is coming next? Well, there is a big number of things that can be done in the future in CMB. And I would say that each item of this list could be perfectly one talk. I mean, you have gravitational waves, B modes. You have Sunyaev-Seldovich clusters, reionization, spectral distortion from the combination. There are many items. I only want to give you a quick idea on one particular item, which is gravitational waves. So if we were able to make a picture of what would be the power spectrum in the future should be something like this. This is the prediction for Planck. So Planck will be able to measure the power spectrum in temperature up to L2000 within cosmic variance with extremely high precision. The same for the E power spectrum, and it should be able in principle to detect B modes if they are sufficiently high. This plot is at the level of 0.3, which is practically discarded nowadays. So why it is important to measure gravitational waves? But you see here where the gravitational waves are appearing in the power spectrum, large angular scale. Well, first thing, obvious, we don't have direct evidence of gravitational waves so far. But there is another critical point connected with the CMB, and it's the fact that if we are able to measure gravitational waves, we will have immediately information about how inflation was occurring. The level of gravitational waves is connected with the energy scale at which inflation is happening. So this will tell us immediately what is the particular transition phase which is taking place, or a hint about how inflation is really occurring. So this is the thing we want to measure. There are many experiments, apart from CMB experiments, that could be able to detect gravitational waves, but you see that the CMB already is reaching a level which is far below what we can get from LISA or LIGO and so on. Just to give you an idea of the difficulty of measuring this. This is a simulation of the CMB with polarization. The arrows are indicating the polarization. This is a simulation with no gravitational wave. The current limit is about 0.3, okay? So I'm going to put another simulation adding a contribution of 0.3. You see the differences in the arrows. It's very difficult to see the changes. There are tiny changes in the direction of the polarization. So this is a very difficult task to do. So how we plan to do that? I'm going to speak quickly about two experiments. One is Planck satellite, and the other one is the Quixote CMB experiment. From the point of view of Planck, the IC has participated building the electronic box of one of the instruments of the satellite. Planck will be launched. Well, it's a satellite of the European Space Agency, will be launched in March next year, and will produce full sky maps at 9 different frequencies, and will obtain power spectrum like I was showing before. I have several pictures of the satellite. You see here the two instruments. The horns which are in the center are the high frequency instrument, the horns around are the low frequency instrument. This is a comparison between Planck and WMAP in terms of just the temperature power spectrum to see what will be the improvement, the relative improvement with respect to WMAP. And in terms of parameters, the idea is that Planck is going to improve by a factor of between 3 and 10 the determination of all cosmological parameters. So this is why normally within the Planck community we usually say that WMAP has confirmed the standard model, but Planck will challenge it. We will have the opportunity to make new discoveries and to test the model at the level of percent or even below for some parameters. The other experiment I wanted to mention is the Quixote CMB experiment. You have heard several times about this, especially in the Day of Our Science. I presented a couple of times already the progress with the experiment. So just to remind you, is 10 to 13 gigahertz, 5 frequency bands, 1 degree angular resolution. It's a consortium of 6 institutions in which the IC is leading the project. And to give you an idea of what we expect to do, this is the determination. Just focus on B modes. Okay, this is the level of B mode detection that we expect after the nominal time, after 3 years of observation with Quixote. If we start to measure now this year, we should have this just before the Planck results appear. This simulation is for the case of 0.1 in the contribution of tensors. Okay, so well, I think I will be finished. I have several movies, but I think I will skip them. Just to tell you the current situation of the project, the telescope is practically finished. These are pictures from last July, but last week we had some pictures of you see, by comparison. This will be the telescope. It's a rotating platform, and the telescope will be able to point. Okay, so you see that there are 2 large pieces, which are these 2, which are already built, and will be sent. This is the rotating platform. It will be sent to the IC in 2 weeks. So we expect to have by the end of October, 1st of November, the telescope which should be already here. The instrument should be practically here by the same time. And well, and last transparency with, I'm speaking about the future of the field, so I need to say something about what is coming in the next few years. Planck will present results by 2012. Quixote, we will have results by 2011, 2012. Probably we will continue doing observations, but what is in the midterm and in the large term? So there are 2 missions that are discussed, not approved yet, but are under discussion. One is coming from NASA and another one is coming from ESA. As I say, they are not funded, so the launch will be not earlier than 2018. But just to transmit you the idea that people are thinking in an space experiment to measure B modes at the level of between, let's say, 100 times better that we can do from the ground. Okay, so these experiments are designed to reach values of R of the order of 0.001. So this is the last slide, conclusion. So I would say that we are in a very exciting moment in cosmology, because in the last 16 years there has been a significant improvement in the measurements, starting from the determination of the first peak, and we are now speaking about high precision cosmology with determining some parameters with high precision. One important thing is that there has been a large number of experiments, interferometers, balloon booms, space missions, which all of them are giving a consistent picture. So all of them are suggesting the same strange picture of 70% dark matter, 70% dark energy, 30% dark matter. However, there are fundamental issues which are still open. We don't know what is the nature of the dark energy. We don't know what is the nature of dark matter. We don't know if there will be gravitational waves, how inflation occurs, and so on. But the bottom line is that in the next decade, in the next 10 years, we will have a significant improvement on this, and probably some of these questions will be answered. So I will finish saying that the future in this field is very exciting. Thank you.
Thank you very much. For questions?
I will take the opportunity of your basic introduction to ask you a basic question, maybe it's a naive one. When we see the cosmic microwave background, we see that the fluctuations in temperature trace the fluctuations in mass. But I guess that this is the baryonic mass. It cannot be the dark matter. Do the dark matter leave any trace in the microwave background?
Yes. Basically, I will go. Basically, the amplitude, the relative amplitude of the peaks is connected with the amount of dark matter. So, if you do an analysis of the CMB alone, you are able to say that there is dark. You can, how to say? You can rule out the possibility that there is no dark matter. I mean, you need dark matter in order to explain the relative amplitudes of the peak. Basically, the idea is that you need potential wells in which the baryons are oscillating in order to have this feature. This is one thing connected directly with the anisotropy. But there is one thing which is even before that, which is just the level of anisotropies. If the anisotropies are at the level of microkelvin, we need dark matter. Because in a expanding universe, the fluctuations are growing linearly with redshift. That means that if we see today's structures, the fluctuations are, the relative fluctuation should be greater than 1. That means that if we go to redshift 1000, if we only have baryonic matter, the fluctuations should be 10 to the minus 3, but the fluctuations are 10 to the minus 5. You cannot explain 10 to the minus 5 unless you have dark matter. You need a huge amount of matter, which is much more concentrated than the baryons, in order to have this huge level of, this small level of fluctuations which can be amplified until nowadays. So I will say that two evidence is coming from the CMB. Just the level of fluctuations and the analysis of the peak, which is pointing to dark matter. Yes, no, I think the level of anisotropies is very, I would say, very direct, because or we don't understand anything about the formation. We cannot have if the anisotropies are 10 to the minus 5, then or the nucleosynthesis amount of baryons is incorrect, or something is happening. The CMB is giving the same amount of baryons as nucleosynthesis, and with that amount you cannot have 10 to the minus 5. You need something else which can cluster.
Just a question of the complement of Quixote to Planck.
So there are two basic points in which Quixote can complement Planck. The first point is that Planck will start to measure from 30 gigahertz and above that. Quixote will start 10, 13, 15, 17, 30 gigahertz. So it is extremely important to have this low frequency information if you want to correct the Planck data from the emission of the synchrotron of our galaxy. The synchrotron is the contaminant which is more polarized, at the frequencies that we expect to measure the CMB. So you need very good determination of the synchrotron, and we plan to do that with the first instrument of Quixote. Quixote will have two instruments. The first one is dedicated to map the galaxy. So the first instrument will be only the low frequencies. The second instrument of Quixote will be dedicated to the primordial science, and we can combine the maps of Quixote with Planck to improve practically by a factor of 2 the level of determination of R. So I would say these 2 points. So 4-round correction for Planck and we can improve like practically a factor of 2 the value of R that Planck will be able to read.
Okay, my question is probably not very much related to your talk, but can you comment on the relation between the arrow of time and the experiment results on the CMB?
The
arrow of time, la flecha del tiempo, with the CMB. I mean, it's all the physics in the CMB is revertible.
I don't quite understand. So there are several processes. For example, the formation of the black body, which is happening at very, very early stages. These are, I mean, in which you may have decay of particles, injection of energy into the CMB. I mean, I do not see. Probably we can speak later about that. I don't understand very well.
More questions? Could you comment on the constraints on the reionization that you can extract from the cosmic microwave background?
The basic idea is that the CMB is essentially, I mean, CMB are photons which are reaching us. So if these photons encounter some electron in the way, they can scatter and they can deviate. So every place where we have free electrons, we will change the picture of the CMB. This is happening in the epoch of recombination. Then the universe, the whole universe becomes practically neutral. So the photons are freely propagating. And when the universe is starting to reionize, when the first stars or first quasars are starting to shine and they are starting to produce bubbles of reionization, these photons can encounter again some electron and will scatter. Okay? So essentially the cosmic microwave background can give you a measurement of the integrated quantity of electrons, of the integrated amount of electrons in the local universe. Given that reionization is occurring relatively close to us, redshift, let's say 10, 6 for the end of reionization, such a scale, I mean, the horizon at the epoch of recombination is subtending from here something like 2 degrees. This is the first peak. The horizon at the epoch of recombination is around here. So all the information that we expect to see from reionization is occurring at large L, small L, large angular scale. Okay, so if measuring the, for example, the polarization, which is tracing how many free electrons you have, you can have an integrated measurement of electrons. The problem is that, I mean, you can have more precise measurements with other type of experiments. For example, studying absorption lines in the line of sight of quasars. Because the CMB is only giving you an integrated quantity. I mean, it's total amount of electrons along the line of sight. So it's, I don't know if this is answering. Yeah. I mean, basically, the idea is that, okay, the idea is that the CMB is not very sensitive to the details of the reionization. This is the basic idea. So you can have a reionization which is everything neutral and suddenly everything ionized, or something which is into stages. I mean, some stars are appearing, then disappearing, then everything is becoming more or less neutral, and then again. The CMB is practically blind to that. The only important quantity for the CMB is the integrated amount of electrons. So once we have measured the integrated amount of electrons, from there we can infer, for example, one second. You see here redshift for reionization 11. this is, for inferring that parameter, you need to assume a model. You can say, let us assume that reionization is instantaneous. Then what should be the redshift at which, everything is neutral and suddenly is becoming ionized? What should be the redshift that is compatible with the total amount of electrons that we require from the CMB? And you obtain 11. But it doesn't mean that the reionization was actually occurring there. You need to do observations of quasars, absorption lines in the Lyman alpha forest in order to infer the details of the reionization. But the CMB is only giving you how many, let's say like a necessary condition. You need, whatever the reionization is, the total amount of electrons should be tau 0.89. Tau is the optical depth to the reionization epoch. So it's just an integrated quantity of electrons. You cannot say more than that.
Yes, my question is related about the detectability of the gravitational waves. You have said that maybe Planck, in principle Planck could be able to detect, but obviously only if they lie in the range of the detector. So my question is, if we have any theoretical reason to be optimistic?
There is a huge number of inflationary models. The inflationary paradigm is something relatively general, but the particular model for inflation, you have many options. You have standard inflation with one single particle. You can have hybrid inflation with several particles. There are a huge family of models. The presence of gravitational waves is a relatively general prediction for all of them. And for the very basic standard model, there is a connection between the tilt of the spectrum, NS, which is here, the fourth parameter. There is a connection between that and the amount of gravitational waves that you expect. N equal 1 means Harrison-Feldovich spectrum, which means a scale invariant fluctuation. If n is different from 1, and we are measuring something which is different from 1, the amount of difference with respect to 1 is connected with r. For that value of n, we will expect something r of the level of 0.1, something that we plan to reach, for example, with Quixote. However, this is the prediction for the standard, for the, let's say, most simple inflationary scenario. It could be that, if you are able to reach that level and you don't detect anything, that means that we can rule out that scenario, and then we have to go to more complicated scenarios.
Last question? No? Okay, so let's send the speaker again.